Okay. Hi, good evening, everyone, and thanks a lot for coming to this revision session for week 7 to week 10 of algorithms in data science. So, I'll just cover the basic objectives of this session. We will cover the concepts which have been used from week 7 to week 10, and maybe week 11 we will do on Monday. So, on that note, shall I start? Can somebody give me a hands up? Yeah, thank you. Okay, I'll share my screen. Okay, I think my screen is visible to all of you. Can somebody give me a hands up? Yeah, okay, thank you. Okay, so week 7 has basically started. I'll just give you the brief intuition. It is started with that if we train a model, we have got some training data set and we have got uh, data here. And if we train a classifier, which the model gets trained to classify these points as 0 and 1, then we want to know, now we don't know the test data set which is there, but we know that both of them, the training and test data sets, they are coming from same distribution. So we are interested basically in knowing that what is error the of the model. For example, this is error S and this is the model we have trained HS. Now, what is the difference between this error and the error of the base model? So, base model is a model which gives you the least error, because if we know the distribution, then we can make the boundaries. For example, if we have got the points and we know the distribution, then we can make the boundaries where the base will give us the least error. But to know this base error, we need the distribution. But the million-dollar question is that we don't know the distribution. We have been given only the training data set. So we want to know that what is the bound on this, that we train a model on the training data set, and what is the actual error. We are interested in knowing this. Is that clear with everyone? Any question, any doubt in this? I'll just give you an example of this Bayes error also. And it is not necessary that a Bayesian error is zero. For example, if we have got data set from a distribution like that, all the negative points are coming from a normal distribution like this, and all the positive points which are there, they are coming from a normal distribution like this. So there will be areas. Now, if we make a Bayes error here, and this is normal, and for example, its mean is -1 and variance is 1. This mean is 1 and variance is 1. So for a Bayesian error, if this is a theta, then we will declare y is equal to minus plus 1 if f of xi is greater than equal to theta, or -1 otherwise. Now you see, in this case, the Bayesian error will never be zero, because there are certain areas, for example, here, there is a probability that point can be +1 also. However, as per this Bayesian, it will be declared as -1. Similarly, this area is the one where it can be, it is actually -1, but it can be declared +1. So this is one condition where for a normal distribution, the Bayesian error will not be zero. However, if there is a linear data set without any noise, for example, these are plus points and these are negative points, then we can have a linear classifier. There is no noise, where the Bayesian error will be zero. But in case there is a noise, for example, there is a 1 -1 point here, and there is 1 +1 point here, then in this case also, your Bayesian error will not be zero. So that concept is to be kept in mind. Now, with that, what professor did, he broke down this into three parts. So this is error of the model which has been trained on the training data set, that is RSHS. This is error by the Bayesian model, which is will give you the least error. So what we can break down this in three parts by doing addition and subtraction. What we can do, we write RHS minus RDHS. I'll just explain all these terms. Plus RDHS minus R of H plus R of H minus R from the Bayesian model. Now this is what? This is RSHS. This is the error of the training data set. This is error of HS, that is a model which we have trained on the training data set. And what will be the error on the test data set? This is the D is the test data set. So this is known as a generalization error. Generalization error. The second is that what is the error of this model on the test data set minus error of the best model from our hypothesis class. So hypothesis class, we have got many models here. H1, H2, H3, they can be finite or they can be infinite. So what is the best model which gives the least test error, for example, H2, and what is the error of my model, which is the model which I have trained from my training data set, that is S. This is known as, can somebody tell me this? What is the name of this?
Approximation error.
This is, no,
Estimation.
approximately the last one. This is also known as, this is, yes, Ravina, can you tell me? This is another name is also there. Professor had covered. I'll just show you from the notes.
Estimation error.
Yes, yes. This is estimation error, which is also known as optimization error. And the last error is known as approximation error. Now we will see this one by one. Okay. So we have to be very, very clear. Again, I will repeat again. We have got a training data set, for example, X1, Y1, X2, Y2, up to Xn, Yn. This X can be any in dimension. For example, I say RD, and Y is a label 0 or 1. And I have got a hypothesis class in which I've got various models. It can be finite, it can be infinite. These are my models. So we are interested in knowing that what is the bound on the error which I get on this model which I train on the training data set minus the best model, which can be a Bayesian model. What is this? So this I have broken down in three parts. RHS minus RDHS means that I select a model, I train that model. What is a train error? And this is test error. So we can call it is train error, and this is test error. The second is test error minus error of the best model from this hypothesis class. Best model error. And the third is, what is the best model error? This best model means best model from H, minus the best model, the Bayesian model, which we could have found if we knew the distribution. So first is known as generalization error, second is the estimation error or optimization error, and third is known as approximation error. Now we will see all these errors one by one. How do we handle that? Okay, so first we come to generalization error. generalization error is error S HS minus error D HS. Now, this model which is there, it is a random model because I got a hypothesis class and there are various models. So any model can be here. So this is a random and this is also random. But for any fixed model, for example, if I fix a model H for any fixed model, then the expectation of air S HS is equal to air D HS. That if I take a model, I fix a model, then expectation of error of that model will be equal to air D HS. Now using this, we can write probability of absolute value of air S HS minus air D HS can be written down as probability of air S HS minus expected value of air S HS greater than equal to epsilon. We know by Hofferding's inequality that if it is less than delta from Hofferding's, this becomes less than e to power minus 2n epsilon square. Is this okay with everyone? Surupi?
Could you just go over this last part again?
Okay. So last part I'm saying that we want to bound our error, which is the error. So this is my model which I've selected, and expectation of this error is nothing but this air DHS which is there. So I have replaced this air DHS by expectation, and we know that Hofferding says that if I have got some here model and minus expected value, and if it is greater than to epsilon, it is less than epsilon, sorry, e to power minus 2n epsilon square. This is Hofferding's inequality. Okay. So we want to give a bound on this error. So I am saying that probability of error of my model, which I've used on the training data set, minus test data set is greater than epsilon. I want to bound it that it has to be less than delta. For example, this epsilon can be that I say my error should not be more than 0.05 and this should be less than 0.05, means I want 95% assurance that 95% of the times this error should not be more than 0.05. This is the meaning. Is that okay?
Yeah.
Okay. Now, if you combine these two parts, 1 and 2, so this was for a fixed model. Now, we know that in our kitty, we have got various models. Okay. So this is my hypothesis class. And hypothesis class, for example, I have got, this is less than infinity. So I say that my best model, which is there, I select my best model. This is my best model, which I've selected. And if this is making an error more than epsilon, it means my all other models which are there, they are also making the same error. They will make at least that same error if it is my best model.
Yes.
Okay. So from there, what comes out that then this probability which is there, this model, this becomes greater than equal to epsilon. This becomes here by combining the probability of all the models, that is my finite hypothesis class, this becomes e to power minus 2n epsilon square. Is that okay? And I am bounding this by this delta. So from here, if we solve this, it means if this h is finite, this is for finite case, this h e to power minus 2 and epsilon square is less than greater delta. This becomes e to power minus 2 and epsilon square is less than delta by finite h. If we take natural log of both the side, then it becomes 2 and epsilon square less than equal to log delta by h. If we remove the make the signs opposite, then it becomes 2 and epsilon square greater than minus ln of delta over h. This I can write down as greater than equal to ln over h over delta, and this will become n will become 1 over 2 epsilon square. So this is the final formula which we should remember. This is very, very important, that for a given epsilon and given delta, if for a finite hypothesis class, if I select n number of training data set more than this, then my probability will come in that bound. Then the probability of E of S HS minus probability of error D of HS greater than equal to epsilon will be less than delta, and n has to be greater than size of hypothesis class. Sorry, this will be 1 by 2 epsilon square natural log of hypothesis class over delta. This is the important formula. Is this okay? Clear with everyone? Conceptually?
Yes. Yeah.
Okay. Now, from here, now this was for finite h, but we know that this hypothesis class which is there, models which are there, it is infinite. We can have infinite models. So in this case, what to do? So professor, he said that, when if we have infinite models also, but in a training data set, if I have got only n data points, for example, 1, 2, 3, up to n, then every data point can be either 0 or 1, 0 or 1. It means the possible labeling which is there, it is only n square.
Yes.
Okay. So now that formula which was there, we had found out that it was less than equal to h e to power minus 2 epsilon square n epsilon square. We can write down that this size which is there for infinite, this can be maximum n square only. So this we can write down n square e to power minus 2n epsilon square. Ravina, this was your question na, in WhatsApp, that how this n square had come. I'm audible, Ravina?
Yes, sir, I don't remember now. I
Okay.
will check.
Okay. So now, so for infinite, if I have got infinite, so from here, due to finite number of labelings, if we have infinite models also, but then probability of R S HS minus RDHS greater than equal to epsilon will always be from this number 2. Okay. Third question was that this n square. So there are very important takeaways from there. First of all, this n square e to power minus 2n epsilon square, which is there, n is increasing and this term is decreasing. And when n tends to infinity, this probability or this entire term will tend to 0. It means the difference between this and this, or the probability of greater than equal to epsilon, will drop down to 0. So it means if we increase the number of data points, I will have good amount of probability. Is that okay? Surabhi, this understood?
If I increase the probability, I'll have good number of.
No. If I increase the n, as n increases, this term which is there, it starts decreasing.
Yes.
If n goes to infinity, this term goes to 0.
Yes.
This term goes to 0 means that my bound which is there, I can give a fair amount of assurance that my this error will remain within this bound only.
It will
Yes.
be tighter.
Yes, Ravina?
No, sir, I was saying that it will be tighter bound then.
Yes, it will be tighter bound, more assurance. I'm saying earlier it was 95% assurance. As this value goes to 0, it means I can say it is 100% assurance that it is within epsilon. That my train error which is there and test error which is there, they will be within epsilon. And I can say with 100% assurance. Is that okay? This concept?
Yes.
Now, this n square also, if you see, n square is also a very large value. Very large value. So again, we can decrease this term by what we do. This hypothesis class which is there, the models which are there, we can use different models, H1, H2, H3, H4 up to Hn. For example, if we use an interval class, if we say that all H1 up to Hn, they are interval class models. Interval class models. Interval class model, what does it mean? That if you are there within this A to B, I will classify you as +1, else I will classify as 0. So by that, what happens? For example, here I will just cover a question. For example, if there are n data points, so we start with n is equal to 2. So n is equal to 2 means they can be classified as 0, 0, 0, 1, 1, 0, and 1, 1. So take an example of 0, 0. Here it is as 0. Here it is as 0. And my interval class is here. So I can represent this with this interval class. 0, 1 can be here. This is 1. This is 0. 1, 0 will be this class, this class. 1, 1 is both are inside. So, but when we increase the numbers, for example, n is equal to 3, then we can have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, when we see by this interval class which are there, I can achieve all these results by just 7 models. That only there are 7 are possible. So earlier I had n square. N square means I had 9 possible labelings. But here, if I take in this, by AB, this 101 will not be possible labeling. Okay. So only 7 labelings will be allowed. Whereas, so by choosing the interval class, I can further reduce, and the reduction is that number of possible classes, number of possible labelings by interval class is less than equal to 2 to power n. So if we fit this 2 to power n, so we had earlier H e to power minus 2n epsilon square. This is for finite. For infinite, we had n square e to power minus 2 epsilon square, infinite. And if we make only interval class, then it becomes e to power minus 2 epsilon square. This is for interval class. So these are the three important concepts we should remember. This is for air of S HS minus air of D of HS. Is that okay? These 3 points? Surupi, any question in this?
No question here.
So, but this is only valid for binary classes. Am I?
Yes, yes, yes. So, Ravina, if you recollect, when we were doing the machine learning, all our models which are there, for example, logistic regression or decision tree, they all are binary classifiers. When we go to neural network, then only our multi-classification starts. But in machine learning, when we want to do multi-classification, then what do? We make combinations of models. Otherwise, every model which is there, whether it is a Bayesian model or a SVM model, logistic regression model, or it is the decision tree model, they are binary classifiers only. But using the techniques, then we convert them to multi-class classifiers. Is that okay?
Yeah, got it, sir.
Yeah. Okay. So these were 3 important concepts which I just wanted to cover conceptually. Now we will just go through the notes and we will see other parts also. And then there was another part which was called the, okay. So this I have covered. I will just go through the notes, revision notes, whatever I have missed. So this we have covered these 3 errors which are there. Generalization error. This is also known as true error or sampling error. Second is estimation error, also known as optimization error. Third is the approximation error. Generalization error, I have done the derivation. And this is the formula which comes out. This is very, very important from the exam point of view. So week 7 to week 8 was this only. Now with this, we can go to the GAs. Week 8 GAs were quite interesting. And, so first question is this. Is this visible? If I will request you to kindly open your GAs also in case of any doubt.
Yes, sir. I'm not getting the same answer as what was in solution.
Okay. Okay. So I will explain. Don't worry. So question number 1, everybody has done. Question number 1, that there is a consider a binary classification problem with on one feature and labels are -1, 1. The marginal probability of observing label 1 is given Py is equal to 1 is equal to 0.5. Therefore, the probability of y is equal to -1 will also be 1 minus 0.5 is equal to 0.5. The class conditional densities are Gaussian. So this is a Gaussian with mean 1, variance 1, and y is equal to -1 and -1, 1. Which of the following is a base classifier? So they have given in the base classifier. So we know that how the base classifier looks like. A base classifier is something like this. That y is equal to 1 if x is greater than equal to theta. I have written a here, or -1 otherwise. So we have to find this a. What is this a? Okay. So at a, the probability of this distribution is equal to probability of this distribution. For a Gaussian, we know what is the probability. Probability y is equal to 1. So this is 1 by root 2 pi. I have removed the variance because it is 1 in both case. -1 by 2. A -1 because -1 is your, this is mean by 1 square. And here it will become a minus -1 because -1 is the mean. When you equate this, so you get a minus 1 square is equal to a plus 1 square, and you get a is equal to 0. So your Bayesian classifier becomes y is equal to 1 if x is greater than or equal to 0 or -1 otherwise. Is this understood?
Yes, sir.
Okay. Second question is, find the Bayesian error. That is, you compute Bayesian error R star D So air star D, like I explained during when I was explaining the in the revision, that these are the regions which will give us the errors. These are the enter your answer correct to two places. So Bayesian error is probability of y is equal to 1 into probability y is equal to -1 when actually y is equal to 1. So what is that region? Region is we are declaring y is equal to -1, but y is equal to 1. So this is the region. So here y is coming from here, from +1. But we have identified this as 0. So anything below 0, I'm identifying it as -1. So this is this error. Into probability of y is equal to -1 into probability of y is equal to 1, but actually y is equal to -1. So this is this error, this portion. So here actually it is -1, but I am declaring it as -1. So probability of y is equal to 1, they have given 0.5, and we found p is y is equal to -1 is 1 minus 0.5, 0.5. Now this error which is there, probability of y is equal to -1, 0, 1, 1. So what we have to do, we have to find z value for this value here and z value for this. This we had learned, if I'm not wrong, during statistics 2. That for a normal distribution, how to compute z. So z is nothing. Z is x minus mu over standard deviation. So and
We didn't.
then
It's why we are calculating z score here.
because then looking the z score, we can find the probability. Otherwise, you cannot calculate this. In stats 2, you remember we used to refer to tables.
So what I did is I in the PDF I integrated it and wrote whole formula 1/√2 pi and
Okay. Okay.
used to put like
Yeah,
that.
that is also good. That is also good. If you are maths, geek, you can do that. Otherwise,
Yes,
using
but it was giving wrong answer. That's why I want to understand this method.
no. So see here, z, for example, there are two z values. One z is coming from here, for example, here. See, you can see visually that both these errors are same, equal.
Yes, sir.
Okay. Now, for example, I find z for here. So I'm interested in knowing this probability. So z becomes x minus mu over nu, and so for p is equal to z is equal to 1 is 0.157. This is from the probability table. Okay. So this is also 0.157 and this is also 0.157. So if you have done through the integration also, I hope you have not taken this. This will become 1 minus integration of this up to here.
Yes, sir. I have taken minus infinity to 1.
Okay. So what you can do, you don't have to take into +1. You have to take only to 0. Because your decision boundary is 0.
Yes.
Right? I'll just explain here for that also. See, this is your both the distributions. This is -1. This is your +1. This is your -1 distribution. This is your, here it is 0. This we found out. This was the first question. It came 0. Now, I am interested in these two errors. So first error is this. First error is here. In this here, actually y is equal to 1, but I'm predicting y is equal to -1. Is this okay?
Yes, sir. And
And
both are equally in both sides.
yes, so both are equally here. So if you want to calculate this also, so what I will do, I will calculate for either for this or this. So for this, if I want to calculate for this, it will be from -infinity to 0, 1 by root 2 pi, and you can put okay, all the figures. So it will be up to 0. So you will get okay, this value. If I want to calculate this value, both are equal, but it will be 1 minus 0 to plus infinity, and here I will use minus 1. Okay,
Yes, sir.
1 by 2, and this will become 1 by root 2 pi 1 by 2 x plus 2 whole square. So this is also you can use it, but I use the z table like here. I hope again this kind of question will not come because integration they have not taught us. If they give the z value, then immediately the answer comes. But this concept has everybody understood? Surupi?
Yes, yes.
Okay. Now we go to next question. So consider a sample S, which is coming from dataset D8. Each element of S is of the form XY. This is the dataset. So these are plus ones and these are minus ones. For a fit a decision stump using entropy as the impurity measure with the question at the root node of the form x greater than equal to theta, where theta belongs to z. If there are multiple values of theta, use the smaller among them. Call this stump HS. Enter the value of theta. So first we have to understand the entropy. What is entropy? So entropy means I have got plus 1 points, I have got minus 1 points. I have got this, I have got this. If I identify all of them correct, then entropy will be 0. Otherwise, entropy will be the ratio of these points which I have taken and how many are incorrect. So that is the concept of entropy. Let's see the data first visually. So visually you see these are the plus 1 points and these are the minus 1 points. So immediately visually you can see that your stump which is there, it is happening at x is equal to 1. But how to do mathematically? So let's take theta is equal to 1, then we can take theta is equal to 0, and we can take theta is equal to 2, find the entropies, and then we can select the theta, smallest theta. And this is the theta is the smallest of them. So let's say when we take theta is equal to 1, then you see theta is equal to 1, then all these points will be identified as positive. It means there is one incorrect classification and these will be identified correctly. So here entropy is 0, but there is an entropy here. So and the value of entropy will be what? Here is 1 incorrect, so this will be 1 by 5 entropy. And what are the how many points are there? 5 by 8. So this is your entropy plus here is 0. So this comes around 1 by 8. Now when we take theta is equal to 2, remove this. When we take theta is equal to 2, theta is 2 here. So here entropy is 0 because all are correct. But here again there is one misclassification. So in this case also it is 1 by 5 into 5 by 8. So it will also give 1 by 8 only. But if we take the smallest theta, then theta out of 1 and 2 is 1. We can check for 0 also. And in case of 0, then here it is correct, but here 2 are incorrect. So here entropy will become 2 by 6 into 6 by 8, which is 1 by 4. And 1 by 4 is greater than 1 by 8. Therefore, we will not select theta is equal to 0. So we did theta is equal to 0, 1, 2. We found they are giving similar results. And we have to select the smallest theta. We have selected theta is equal to 1. Is this okay with everyone? Okay, let's go to next question. Okay. So for next 5 questions, note that S is not random. S is the training data set which they have given to us. Treat HS as a fixed deterministic classifier and find the train error of HS. So we have found HS and we found theta is equal to 1, and we know then they are asking us to compute the train error. So already we have calculated there was 1 point misclassified. So it will be 1 by 8 because 1 is in classified. So 1 by 8 it comes 0.125. Second is the find the test error. Now test error, we know that distribution is actual distribution which is there. It is following Gaussian -1 and 1. So your test error will become LDHS is equal to 0.5. Again, the same concept, it will come. But now here we have to find for theta is equal to 1. Earlier we had selected for theta is equal to 0. So for theta is equal to 1, it means I have to select for y is equal to 1, but actual y was -1. So for this -1 which is going here, this is the area where actually y is -1, y is +1. This is the area where y is -1, but we are predicting it as y is equal to 1. Similarly, y is equal to predict y is equal to -1, where y is equal to 1. So this will be this area, the entire area here. This is the area where actual y is +1, but my theta is 1. That's why I'm predicting everything here as -1. So these are the errors. So again, I did what I did. I calculated z values for both. So for one, z came 0 because for one, theta is 1. Here it is 0. For second was 2, this value. And seeing the probability for z is equal to 0, it is z is equal to 0, it is 0.5, this here. And z is equal to 2 was 0. Minus 0.228, this one, very less value. And then using the formula, we got 0.261. So this is your test error of ESHS, the model which you trained, and on the test data set, just to make the concept clear. Is that clear with everyone?
Yeah.
Okay.
What happened?
Hi, am I audible?
Yes.
Yes, sir. Yes.
Okay. Okay. Sorry, I'm having some net issues. So where I was, could you that understand that point of how that air d h and minus air star was zero? I will just share my screen. Okay, yeah. Hi Rajesh. Okay, so I was explaining this. I hope I was able to complete this. How it came zero. Anybody any question in this? Surupi?
Could you just go over it one more time in brief?
Okay, okay. I'll just. Okay, see, your approximation error is nothing that error of your best model, which is from your hypothesis class, minus error of your Bayesian error, error star. Now, Bayesian model, we already obtained for Bayesian model, theta was 1 and your error was 0.261. Now, here from H class, which is there, it will have all stumps 0, 1, 2, 3, all stumps which are there. And we know that best model which was there, it is stump is 1. So here also we will get the same model, which is giving error 0.261. Theta is equal to 1. Now when I subtract this, it will become 0. Is that okay?
Yes. Yeah.
Okay. Now we go to next question. So, but the point to note here is that it is not necessary that your best model will give zero error. Your best model also can have error. So that was the point. Now, next question is, let the hypothesis class H be the set of all decision stems. Compute the absolute value of the estimation error. So estimation error we know is the error on the test data set with your model which you have obtained from the on the training data set. So here we have obtained theta is equal to 1. Estimation will come 0.261 minus LDH. Now this LDH which is there, the best model for base here this air is we are getting from H. Here we got base at theta is equal to 0 and error which we got was 0.16. So here your estimation error becomes 0.261 minus 0.16, 0.101. Okay. Now we go to the next question. Next question, they say that we have got weights and we have got heights and we have flattened them. We don't know what is weight and what is height. But they have given that height and weight, they are coming from this distribution. So this is a similar question like we have solved just now. This is height, this is weight. They have given variance. Respectively, from this you obtain the base optimal classifier, which effectively finds a threshold theta such that if input is greater than or equal to theta, then it is classified height or it is classified weight. So see, this is your for weight. Weight is following N6510. The mean is 65. These are your data points. And here it is your height. So this is your theta, that if it is more than this, then it is okay. I have done opposite. So here it will be like this. Here is weight. Okay, it is correct. So it is greater than or equal to theta, then it will be declared as height or weight. So it is correct. So we have to find this theta. So again, what we have to do at this, the probability of this distribution will be equal to probability of this distribution. So we use the same formula, Gaussian formula. And when we solve the quadratic, so it here another important point comes that when we have got Gaussian distributions, then we get quadratic solution. quadratic solution. So this is for height, this is for weight. We equate 2 pi root 2 pi cancel out. We get a quadratic equation. When we solve that quadratic equation, we get two values. One is theta is 132.8, second is 291.2. So then we see our data, 291.2 does not make any sense. So our correct is 132.8. So above 132.8, we will classify it as a height. Less than that, we will classify it as a weight. This was that question. Next question is distribution D can be modeled as follows. Toss a coin with bias is equal to P to decide on gender. Sample height weight from F, Y is equal to gender, whatever gender you get, then you sample it, height and weight from there, which is a multivariate normal distribution. So this is a multivariate normal distribution which is there. Suppose a classifier is learned by fixing a hypothesis class H, which of the following is true. H is equal to linear gives zero approximation error. This is not correct because here we cannot have linear classifier. H is equal to quadratic gives zero approximation error. We have seen earlier in our example that we had got air H minus air star is equal to 0 and it was following normal distribution. So this is correct. A choice for H exists such that approximation error is 0 because yes, this is true, therefore this is true. There exists no H such that approximation error is 0. This is incorrect. We know that there is a model decision stump at which the approximation error is 0. So this is the question we have done. Next question was that we have got this data set in this grid. Anything which is in the yellow region, which is +1, or in this it is 0. And then they have given us, you obtain the following training data set. This is the training data set. So these are all +1s and these are all 0s. Then they have asked different these values theta, and they have asked that what is the which theta will give the lowest generalization error. So generalization error, we know it is nothing but train error minus test error. So let's see them one by one. So first we see for theta is equal to 1, 1. So theta is equal to 1, 1 will become something like this. And your decision boundary becomes like this. So see, here there are two misclassified. Here there is one misclassified. So there are total 3 misclassified points are there. Training error will become 3 by 8. For test data set, if you put the same model, so it is dividing everything in half. So there is a half probability that this will be misclassified. Therefore, your test error which is there, it is 0.5. Half points will be that. So generalization error becomes 3 by 8 minus 0.5, which is minus 0.13. So this is for 1, 1. Same exercise we do for now 1, 0. So 1, 0 is here. This is 1, 0. So all the points on the right side, they will be correctly classified. And here the test error, training error. Okay, sorry. This is your decision boundary. So all your training points will be training points which are there, they are classified correct. So your training error is 0. But your test error which is there.
So
Hello?
I'm not able to understand how you are calculating test error.
Okay, test error you have to calculate, for example. See, this is your point, and all these points you are classifying as +1, and you are classifying here is 0. And you can see they all are symmetrical. So half of the points which are there, they are incorrect. Here also half of them, they are incorrect. So how out of 1 to 8, out of 8, 4 are incorrect. Here, if you
4 by 8, yes, I got it.
okay, did you get it, Ravina? Hello.
Yes, sir. Sir,
Okay.
I got it, sir.
Okay. So now see here, train error is 0. So your generalization error becomes 0 minus 0.5. It becomes minus 0.5. Similarly, you come to third one. Third one is this point. Your decision boundary is here. So your train error, again, it becomes 0. And see, again here, if you see symmetric, again your test error is 0.5. Okay. So again, your train error minus test error will become minus 0.5. And third also, it will become the same. You get the decision boundary, train error. Here again, you get the same. So these are the 3 points which are there, thetas, for which you get the lowest generalization error. Okay, minus 0.5. This was how. Okay, next we come. What is the approximation error incurred when the hypothesis class is H is set to the class of linear functions? So approximation error is nothing. Any linear class which is there, it will divide into 2 parts. Like we have seen in all the parts we divided, and your test error which was there, it was in all the cases, it was 0.5. Whereas the best base error which was there, which we selected, it gave us a error of 0. So your best approximation error will be at 0.5. So this we have seen from all the 4 examples. So with this, I have finished week 7 and week 8. And I think, in my opinion, we should stop here. We can have a session, next session for week 9 and week 10. But before that, again, I will explain these important concepts which are there. Because see, the questions will come on concepts. So first concept which I explained was that this one is very, very important. Error of SHS minus error of star this. This error SHS is your training error. Training error. This is of your error of Bayesian model. Error of Bayesian model. This is not necessarily 0. Not necessarily 0. If there is noise, then it will never be 0. If there is no noise and there are clear boundaries, then it can be 0. Now, to understand this training error, we have got data set x1, y1 up to xn, yn. We have got a hypothesis class. We have got various models, h1, h2, h3 up to hn. We train any model, or we say what is the best model we have trained, best model we have got. We are interested to know that what is the probability of that this error which is there, which I have got from my training data set, and the best model, Bayesian model, which is there, it is error is maximum absolute value plus epsilon or minus epsilon is less than delta. I want to keep a bound, and with this is assurance. This is the probability assurance. So if I say 95% assurance, then this delta becomes 0.05. And I say that the difference between these two errors is not more than, for example, 0.01. So for that, what do? I break down this error in 3 parts. The first part is error SHS minus error DHS. It means I got a model from my hypothesis class. I trained on the training data set, and I get this is training error. And then I use this same model on the test data set. This is test error. And this error, total error, is known as generalization error. Or this error is also known as sampling error. Because if I collect incorrect samples in my training data set, then this will increase. And what did I achieve? I achieved that probability of this error, RSHS minus RD of HS, is greater than epsilon. This is, I want to keep less than equal to delta. What I did, I fixed one HS, and then I did expectation of this HS. And from there, then I said that if my best model is making a mistake, then all other models are making a mistake. And from that concept, I got probability of error of SHS minus error of DHS greater than equal to delta is less than equal to 1, the dimension of H finite epsilon e to power minus 2 n epsilon square. This came from Hofferding's. And now comparing this 1 and 2, we got H e to power minus 2 n epsilon square is less than equal to delta. And from here we got n is greater than equal to 1 by 2 epsilon square natural log of H over delta. So if I have number of data sets which is greater than this, then I can say with assurance that my error, training error and test error will not be so far away. This was first takeaway. So this is very, very important. Second was that if in case my H is not finite, which is the case, H is infinity, because we can have infinite models. Then we said that model can be infinite, but I have got if data set is x1, y1 up to xn, yn, then the number of labelings which is possible is only n to power square. So this term which is there, h e to power minus 2 epsilon n square, it gets converted to n square e to power minus 2 epsilon n epsilon square. And if we fix the class of our models, for example, interval class, then it becomes 2 to power n epsilon 2 n epsilon square. Main takeaways from here, all three, is that as n tends to infinity, this value tends to 0. So I can say with 100% assurance that my error, which is the train error and test error, will differ by epsilon with 100% confidence. These are the main takeaways from week 7 and week 8. Any question till now? If there is any question, I will answer. And like I said, we can keep week 9 and week 10 maybe for Monday. So let's grasp these concepts. And with these concepts now, you see your GAs now. And everything will become clear. With that, can we stop now? Otherwise, I think it will become...
So, sir, I have a question.
Yeah.
Sir, can you share the screen once more?
Yes.
Sir, can you draw a few points, data points?
Okay.
Dot. I
Okay.
want to ask something.
Okay. Yeah. So I have got, for example,
Okay, sir, and some red points also, but yes, sir, but 2 red points, yeah, there. So, sir,
Yeah.
can't we make a boundary which
Yeah.
is like an oval shape, like, and which is just cutting nearby those 2 red points, and can classify this as an like without any misclassification? Isn't it possible that the base error is 0, because we can mold the lines whatever way we want by increasing its polynomial degrees? So
Mhm.
I was thinking like this,
So you're right. See, we don't know from which distribution this is coming. First point is that we have been given only this train data set.
Okay, sir.
Now, in actual, for example, I will give you an example. Now we have done this. So this might be like this. Actual, your test distribution can give you infinite points.
Yes, sir.
Okay. So this is your actual. And if it is following a correct distribution without any noise, then you are right. Then we can have your air star, which is there, air star can become 0. But if there is a noise, for example, in this here, there is a positive point and there is a negative point here. This we call it as a noise. This is
Yes.
a noise. So in case of noise, your air star will not be 0. I hope I was able to explain.
Yes, sir. Got it, sir.
Yeah. Okay.
Thank you, sir.
Yeah. Any other question? Preetham?
Yes, sir. Hello.
Okay. Yeah, Surupi, any question? Rajesh? Parnika?
No questions, sir. Thank you.
Thank you.
No, sir.
Okay. Okay. So with that, okay, I will finish. Maybe on Monday, I will conduct a session for week 9 and week 10. And one day I will keep for week 11 because week 11 concepts are entirely different. Okay. So today we have understood generalization error more in detail. So thank you. Have a very nice day and thanks for joining in. All the very best. Have a nice day.
Thank you, sir.